All right, so I really appreciate you inviting me here today. Well, you didn't all invite me here. Marco, Nikolai, and Nick invited me, but it's really good to be here. This is a fabulous workshop to have seen evolve over the last few years. So during those years, I've had the real pleasure and honor to work with some really smart people who spend a lot of time working on programming languages and compilers for a living, and such as Nate Foster, Dave Walker, Mihai Budio, and a few others. And I should be really clear up front, I am not a programming languages person. I'm a networking guy. But what's really good about this is bringing together the two communities. So I'm not going to embarrass myself today by trying to talk about the design of a programming language, and instead I'm going to give a talk that I think really follows on from a talk that I've given dozens, maybe hundreds of times over the past 10 years about SDN. Because I think of this as a sort of as a continuation, and I'm sure you do too. And a lot has happened in networking over the last 10 years, as we've all seen. You know, we can take it for granted, or those who build networking systems or build networks can take it for granted that they can now decide how their network is controlled. They can write, they can commission, they can buy, they can download from GitHub the software that will control how their network behaves. And it's quite a radical departure from how things how things were used to be. In 2010, roughly, there was this rumor going around at SIGCOMM and other places that the big web scale companies were starting to build their own networking equipment. Well, now all the big web scale companies build their own networking equipment, and we don't really think anything of it. And even companies, AT&T, China Mobile, etc., appear to be building their own networking equipment as well. So networking is changing quite a lot right now. But from the beginning of this whole sort of SDN journey, I had this nagging doubt that we were selling the larger community short. They're selling a bit of a crock. Because I thought that they would eventually come to realize that if you can't change how forwarding takes place, you're not really in control of the network. Because what is a network but something that transfers packets from one place to another? You know, we dress it up on all sorts of fancy stuff, right? But that's really what a network is. It takes a packet from here, sends it over here, and modifies it along the way. If you can't change that behavior, then you're not really in charge of how your network behaves. So over the last few years, starting in about 2011, I wanted to try and understand why it was that we couldn't change the behavior. Was there something fundamentally wrong with the architecture? Was there something fundamentally lacking in the ASIC technology? Was there something missing in the languages and the compiler technology? And I was lucky to be able to team up with this great group of folks from TI, which led to the RMT paper in 2013, describing what's now called the Pisa architecture. And since then, I spent the last 3 or 4 years talking to a lot of people who are trying to build networks and exploit programmability. So rather than give a technical or fail to give a technical talk about programming languages or compilers or even chip design, I thought I'd spend the time this morning to share some of the things that I've picked up and observed in that time, talking to people who are building networks about why it's useful to them, why I think this is happening now, both from the point of view of a trend, a bigger trend, but also from the underlying ASIC technology, why it is that the time seems ripe. But I'm going to start with a cartoon picture that I've used many, many times to motivate why programmable forwarding planes change how we think about networking systems. It's a cheap shot, but I think it captures the idea well. So this is a cartoon picture of the inside of a switch or router, rather simplified view. Runs a switch OS, which today is almost always a variant of Linux or BSD, and the switch OS is going to talk to the processes that sit on top that run the individual protocols that implement a feature. So now imagine it's 2010. And people are asking for VXLAN. For those that don't know, VXLAN is simply a way to tag packets so that you can identify in a virtualized data center which tenant they belong to. So the switches at the time, which are built out of fixed function silicon, didn't have this capability. So the equipment vendors, or the people that were wanting to build this, needed to figure out how they would add it. So first of all, of course, they've got to write the VXLAN software to control the switch, and so they then need to update the driver in order to be able to add whatever capability of talking to the chip. And maybe that takes a few weeks or a few months to do. And then they need to update the switch ASIC because VXLAN involves processing packets in a different way, requiring new types of lookup table. So in the case of VXLAN, that took 4 years. It was 4 years from when it was first defined until it first became available. So the question is that just because it's a kind of a niche application in a very small part of networking? Well, it happened to be in the most invested in, the most profitable, the highest volume part of networking, and it took 4 years to change. So I know it's a kind of a trivial example, but I think we really have to examine why is it that networking is held back or slowed down by the difficulty of bringing about change. So let's think about what happens during those 4 years. Just to belabor the point, but I think it actually does matter because it says something about how our industry works. First, the people that own the network have to identify the problem. Right? So they go and tell the equipment vendors that they need a new capability or a new feature. They tell folks like Cisco, Arista, Juniper, who then huddle at the IETF to try and figure out how to come up with a standardized way of doing that. Why do they do that? Well, they do that because they're making an enormous investment, because it costs tens, maybe even $100 million to make the change to that switch hardware. And if they're to do that, they need to convince themselves that it's worth that investment. So they need a standardized way so that they don't all do it differently and then discover that nobody wants to buy it. Okay, so they go off and talk to their software team to find out what it takes in order to make the change, and probably within a few weeks or maybe a few months, they'll come back with something. So the next port of call is the ASIC team. They ask them how long it'll take, and that takes years, and so the whole process takes years to do. So if you're building a network for whether you're Google or AT&T or somebody that's building a network, the equipment vendor can't just send you a software upgrade for that behavior. Those new forwarding features take years to develop. By then, you've probably figured out a kludge in order to get around the limitation that you were trying to fix. Your network gets more complicated, gets more brittle, less reliable, and eventually when the upgrade is there, it either no longer solves the problem you originally had because you've now changed how you do things, or you need an entire forklift upgrade to replace your network at huge expense. Right? I think I don't need to persuade the crowd here. Right, I'm kind of preaching to the choir. This is a really thoroughly broken system. Right? And we could talk a lot about how we got there and the commercial interests that benefit from holding it that way. Right? But that's not the purpose here. But I think the observation is network systems are built bottom up. And what I mean from this, I mean, it is kind of crazy. It all stems from the fact that you go and look for a switch chip that roughly fits the features that you want. It comes with a data sheet, as chips tend to do, that tells you this is how I process packets. That's written in ambiguous English that tells you what it's attempting to do by reference to RFCs that are also written in an ambiguous fashion. And then from that, you're told what it is that it's capable of, and you hope that it roughly matches what you set out to do. So what you can think about this movement towards programmable forwarding, P4, etc., is trying to turn the way that the network is designed on its head. So the goal is really to try and enable anyone who builds a network system to program the system top-down by telling the forwarding plane precisely what they want it to do, In some kind of language, P4 is clearly one that's gaining prominence, but of course it's one of many potential languages, just like I do on my computer. So it seems kind of obvious that this is the way that you would want to do it. So it begs the question, why weren't all the systems built this way all along? Okay, so what I want to do is go through a sort of a sequence of questions, or try and answer a sequence of questions. Why programmability is happening now, why I think it's happening now, how it's being used, and then why programmability is happening now from an ASIC viewpoint, from the underlying chip technology viewpoint. Let's see how this goes. By the way, in the background, you should be mindful of this, which is just happening somewhere out. Oh, hang on. No, it didn't appear on my screen. There's a picture of the eclipse, but I'm obviously mirroring it incorrectly. All right, I won't try and flaff with that right now. Gives me a bit of time to move. I think it's happening right over there, isn't it? Okay. So one thing is that the networking has been kind of living in the dark ages, and you could think of it as trying to catch up with the rest of technology, right? So we're all very familiar with this model here, and I can remember when graphics cards were fixed function cards built by people like Sun and DEC and IBM, and then all of a sudden the GPU came along, and we take a domain-specific language, a compiler, a domain-specific processor, and graphics was never the same again. Same thing happened in signal processing. I can remember when video codecs or radars were built out of fixed function signal processing. You would never do that today, because what came along was languages that you can use for expressing signal processing that lend themselves to efficient description of an FFT or something like that, compilers, and then blazingly fast signal processors, DSPs, that now totally dominate that space. We've seen it happen more recently with machine learning, with the TPU, with TensorFlow as a domain-specific language, compile down, run on the TPU for machine learning. So what happened about networking? We saw these things called network processors. You remember NPUs? Well, NPUs were not really a domain-specific processor, because in all of those other cases, somebody stepped back and said, what's the right instruction set? What's the right data model? Let me redesign a specific processor for this environment. NPUs borrowed the name for something which was really a collection of RISC cores thrown onto a piece of silicon that you then had to painfully microcode in order to try and get it to fit, get your functions to fit. It wasn't really rethinking the problem as a domain-specific processor. So it's not surprising that it didn't really work out too well. So today, there is an example. I don't want to make any claim that it's the right way to do it or it's the only way to do it. It's just the one that seems to be popular right now, and that is the P4 language compilers, and then this Pisa architecture, which is really a more easily pronounced version of what was previously called RMT. So you can think in many ways of this Pisa architecture as attempting to bring to networking what RISC was doing to computing. It's a bit of a cheap analogy, but in the sense of trying to boil down the operations that you would use to process a packet into a basic set of instructions and operations, and a heavily pipelined model that would lend itself to a very high issue rate or throughput. But essentially, it's designed to be a compiler target. The idea is that it's very uniform. This is the PowerPoint simplified version, but it captures the rough idea. An identical set of pipeline stages, and each of those pipeline stages is designed to perform a single set of match in action that can all be done in parallel. So within one stage, the vertical stack represents blue for memories, where the matches would be done, and then actions that are performed in ALUs. There may be dozens, there may be hundreds of those, depending on a particular implementation. So the match in action being performed like that. And then you go through a sequence of them in a way that I'll show you in a minute. Parser at the beginning, or the thing that's doing the typing, is declaring which headers are going to be recognized and which might then later be created by this pipeline. So the programmer then declares what tables are needed and the how packets are to be processed by means of the program, for example, a P4 program. One of the key attributes of this that I've observed along the way is the importance of uniformity. If you're trying to design a compiler, and I'm sure many of you have, you'll kind of appreciate this, how hard it would be to design a meaningful compiler that would work across a variety of different targets if all of those stages were different, either in size, scale, or function. And so by making them absolutely identical, at least as an abstract forwarding model, and hopefully actually in its physical implementation, it makes for a much easier and simpler compiler target. And this is one thing I learned from a guy called Pat Bossart, who was the original architect of this approach. He says, I'm not building a chip, I'm building a compiler target. And that's something that to bear in mind. So the Pisa chip is initially blank. It doesn't know about any protocols. There's no protocol encoded into the chip itself. The P4 programmer will tell the programmable parser what packet headers to expect, and it'll tell it how to process those headers after they've been pulled out of the packet. So let me give you a sort of simple animation view of how this would work. Here's a packet coming in on the left-hand side. We know packets have data and then a sequence of headers, the different colors just representing different headers on that packet, maybe IPv4, IPv6, TCP header, Ethernet header, etc. So the parser you can think of as identifying those headers from a chip point of view or from a forwarding point of view. It's extracting those once it's recognized them, and then placing them onto, logically and in practice physically, a very wide bus that then will carry those as to the match action stages. So in the first match stage, those blue boxes representing the memories will each have these packet headers steered to them, and then they will be processed as a match action, generating a different set of headers. So you can think of it as a transformation, maybe even a geometric transformation of the headers from the input to the output. You may create new headers for encapsulation. You may destroy headers for decapsulation. You may switch them around just for fun. You may decrement a field. You may update a checksum. Those are things that you would do in that match plus action stage. And then as you go down the pipeline, then the sequence of operations would take place. Why is there more than one? Well, there's more than one just because of the serial dependency that might be present in the program. You might have to do one after another, and so that's why you would have multiple stages as you go down. And then eventually you end up with a set of headers at the end, which may or may not look like the ones at the beginning, which then get put back into the packet and then sent on their way. I'm going to make one mention of Barefoot, the company that I've been working with for the last couple of years, only to say there is one instance of this now. There will be other instances in the future. Just to say this is fairly concrete. I'm not here to tout this particular technology. So how is this programmability in general being used? What are the things that people seem to be using it for? So the first thing is which came as a little bit of a surprise to me, rather than add stuff like new VXLAN headers, the first thing people seem to want to do is to take stuff away. Because, and this with hindsight is kind of obvious, if you have a fixed function piece, I've got to use my microphone, sorry. If you've got a fixed function piece of silicon and it takes you a long time to develop it, you have to put many protocols in there that you think cover the entire set of what everybody wants to use. But any individual user only wants to use a small subset of them. So a typical fixed function switching chip might have 40 or 50 different protocols supported, of which the typical user might only use 3 or 4. So they're carrying a very large burden in their network of protocol behavior, which is not useful to them, which is occupying the resources of the switching chips themselves, but also can potentially go wrong. And I've heard anecdotes suggesting that many of the faults or problems that people have in large networks is caused by protocols that they didn't even realize were running and that they didn't know that were using because they were present and they didn't have an opportunity to remove them. So if you think of it in an environment like this, where I have a program describing a switch, there is a program called switch.p4, which you're all welcome to look at on the p4.org website. It's an open source program describing the typical forwarding behavior of a switch that you might see in a big data center. This is a set of features that is in that open source program that a number of people have contributed to. It doesn't matter if you know the protocol soup here. Well, the only thing to notice is there's a lot of them, And so typically what people want to do is to remove many of the ones they don't use. Right. So one thing we've observed is you give somebody switch.p4 in order to use in their data center. They say, how can I comment out all of these other features that I don't want? And then I compile it. And at the time that I compile it, then I will run it and put it into my chip. So this is kind of the first lesson, and the first observation is that programmability gives you the opportunity to remove the stuff that you don't know, and the burden that it provides in terms of reliability. It also means that any resources that were dedicated to protocols that you didn't use now get freed up for those that you are. Bob.
It's also a lesson in kind of shows that networking communities kind of can learn from programming languages, in this case, modularity and the ability to compose.
Yes. Anyone that's played around with a P4 programming language will quickly come to the conclusion that it's not as modular and composable as you would like. But yes, it certainly points to the necessity. Yes, absolutely. So the other thing that people clearly want to do is to add proprietary features. So this didn't used to happen. This is what the sort of the control flow graph might look like for a switch for about 20 years ago. You basically had to decide whether it was an IPv4 or an IPX packet. That was really all it needed to do. If you take the control flow graph for that switch.p4 program, this, you can't see it on the screen here. This is only a sort of a small subset of it. And if I actually expand it out, that's one portion of one area of it. It's about a 4,000 line program that explains and describes the typical protocols that you would see in a fixed function switch today. So the thing to notice here is it's crazy complicated. Right? First of all, you can see why people would want to remove stuff. You can also see why it's extremely hard to verify the correctness of a fixed function chip. It's just becoming horrendously complicated to do so. What it does mean, though, is new stuff is being added, and people are adding new things as they go. And these are kind of examples of things that I've observed people trying to add so far. The one thing that you would expect, new encapsulations and tunnel formats, like VXLAN, the one that I described earlier. New ways to tag packets for special treatment. New approaches to routing, for example, source routing in a big data center, or segment routing is one that you've probably seen. New approaches to congestion control. If I can actually have the switch perform a behavior that is private to me in my big data center, that allows me to treat congestion control faster or in some better way, for example, tagging packets with the occupancy of queues, etc., then you can see how that would be beneficial. New ways to process packets in networks. People in financial, in sort of high frequency trading, I've seen them trying to figure out how they can process ticker symbols. Not something particularly interesting to me, but once you have that capability, then people will try to use it. Some other examples so far. There are a couple of papers here this week, so I pointed these out. For example, building a layer 4 load balancer. So layer 4 load balancing is primarily about maintaining the state of a very large number of connections and the mapping between an external IP address and an internal IP address. Tracking and maintaining a large number of these is a natural extension to what we would place in the network. I think of this as just a natural extension of routing, one that's been difficult to put into a network in the past, into a switch in the past, because it turns out that the people who own large networks typically run their layer 4 load balancers in slightly different ways. They've got some private or local behavior that has been placed into these complicated, expensive commercial boxes over the years. If they have the chance to change that and tailor it to their own specific needs through programmability, then there's usually a simple way that happens to fit in their environment. Fast stateless firewalls, people who just use firewalls for inserting very large numbers of ACLs very, very fast, for example, in a large enterprise network, then something like this can fit quite well for them. A cache for a key value store. There's a nice paper on called Netcache which actually won't appear this week. It's in SOSP a little bit later in the year, about caching portion of memcache packets in network for a large number of servers that sit behind. So another use, which sort of gets back to the trying to get away from the problem of fixed function silicon, is trying to drive silicon independence. For any of you who've heard Amin Vadat talk over the last couple of years, you'll have heard him this mantra of, I'm trying to design a very large network, and in my network I want to be able to think of the switches as dumb peripherals which are controlled from a control plane, in their case an SDN control plane that sits outside of the forwarding plane. And I'd like to be able to think of all of the switches as just performing a function that I've told them to do, rather than them telling me, and for them all to behave in exactly the same way under my control. So Google, Barefoot, ONF, and some others have been working on this thing called P4 runtime, and an open source project to remotely control P4 switches. And this is a fairly sort of creative way of thinking how you could break the dependence on the particular feature set of individual pieces of silicon. So you think of an environment like this: lots of top of rack switches running a switch OS, and then where you would have in the past seen OpenFlow sit, which is fixed and static and supports a fixed set of protocols, a fixed set of match and action primitives. Instead, have the ability to insert a P4 program from a remote control plane down to the switches to tell them the behavior that you want them to have at runtime, and to be able to update and modify that as you go. Problem with doing this typically is that by changing the forwarding behavior of the switches, you also change the behavior of the control plane, because it now needs to modify its behavior because of the new forwarding behavior that it's just instructed. This is much easier to do and more practical to do if you're doing it top down, because if the control plane decides the behavior that it wants, then it can tell the switch to have the forwarding behavior that it needs in order to get its job done. If it goes the other way around, it's much less likely to work. So the idea is that to have a single channel, in this particular case a gRPC channel, doesn't really matter the details, down which a P4 program would be pushed. This will modify the data model that you're using to control the resulting tables in the forwarding plane. But if you've actually got a fixed format in which you're changing the data format through a data model representation, then you can then constantly update that behavior without having to rip down the channel over time. Yeah?
So the OpenConfig work is around data model. It's not really P4, right? So that means that P4 runtime will produce data model, which will go over gRPC, and then data model will be associated with forward.
This is really comes about because the OpenConfig is really there just to be able to switch ports up and down and to install new programs, because it's, if you think of it, it's operating at a slightly sort of... Yes, yeah, that's right. And so...
You are not transferring P4 bytes, you are transferring data model to the device.
That's correct. That's correct. And then after that, you're using that as a way to refer to those particular tables that you've just described. And so you got it in a programmable switch. You've got a control, sort of a control flow behavior that's implemented by a set of match action tables, and those match action tables are described in the program itself. And so once you've described those tables, at runtime, you need a means to talk to them, to be able to communicate to them. And that behavior you've just determined by the program you've just loaded. And the API that would normally be used to talk to a switch is the one that is that is operating quickly at the runtime of the switch. So now that you've described the behavior of the tables, you now need to know how you're going to communicate to them. That's what you represent through the data model that you then agree upon for the communication between the switch and the control plane. And then the control plane is up and going, and then it can use that in order to be able to update and populate tables, change configurations, etc. And the reason for adopting OpenConfig is just that it's an open way of doing that already. So the idea being to drive silicon independence and then a program independence. in a way, not a surprising consequence. Perhaps the surprising thing is that this appears to be happening maybe a couple of years earlier than I would have certainly have expected. If you want to learn more, there was a talk at the P4 workshop back in June. Another way in which programmability is being used is for telemetry or measurement. You may have heard me talk about this before. In some ways, this has turned out to be the sort of the most immediate need. Everybody in our industry right now is talking about how they can get better measurement into the behavior of the network, better visibility into how the network is operating. So let's just take a step back for a moment and think about how we have visibility into our networks today. And I want to actually pose this as a set of questions that it would seem natural to want to be able to answer in a network. So if you think about how we answer questions about visibility today, what our network is doing, the tools that we use, ping, traceroute, SNMP, are essentially the same tools that have been used for about 20, 25 years, right? I would argue that the reason that they haven't changed is because those who own and operate networks haven't had the ability to change the behavior in the network to tell us what it's doing. They've had to live with the things that other people have implemented. So just taking a step back for a moment, what is it that you would really like in a network? So let's take this network of set of servers communicating with each other through a cartoon representation perhaps of a data center network. So between those two servers, a set of packets are flowing, and I would like to be able to take one of those packets and ask that packet, which path did you take? Which path did this packet take? In other words, I'd like it to tell me, I touched this switch at a certain time, I touched another switch at another time. You're all thinking, doesn't ping or doesn't traceroute already do that for me? No, it doesn't. It tells you which the probe packet, the path that it took. It doesn't tell you about the data packets in the network. And we're all familiar with the problems that you might encounter. And it's kind of funny, isn't it, that we use traceroute, and we've used traceroute for a long time, because it was a clever hack on a mechanism that had been put there for something else. It wasn't designed in order to be able to identify which path the packets took. I'd also like to know, in addition to how did my packet get here, I want to know why it got here. What are the set of rules that it touched upon in the switches that meant that it actually ended up here at the point that I probed it? In other words, if you think of a set of rules that are in those switches along the way, which rules did it touch? So I'd like it to be able to say, I touched this particular rule in one switch and this rule in another switch. You can ask the question, why doesn't the packet carry that information? All right, our CPUs, DSPs, all of the most domain-specific processors have specific way of carrying the information that allows you to see the behavior and the consequences of a program. Right? Our networks don't do this today. That's it from a functional point of view, but what about from a performance point of view? How long did my packet queue at each switch along the way? In other words, why can't it tell me I queued for this amount of time at one switch, this amount of time at another switch? Just think how easy congestion control would be if all the packets told you exactly how long they queued at each switch along the way, right? We would change the way in which we would design congestion control. It would be nice if we could take this one step further. In addition to the time occupancy of the queues within the switches, and actually have the packets tell us who they shared the queues with. Because at the end of the day, the performance of the network is largely dictated by the queuing behavior. If I know the queue occupancy that this packet saw, but also the queue occupancy of every other packet, then from that I can determine who was in the queue at any particular time. And therefore, if I was being treated badly, who was it that was treating me badly? And so I can go and talk to them. So if, for example, I had a breakdown of the time occupancy of the queue, here, between the orange and the green, I'm the green flow, I'm actually fine, I'm very well behaved. I need to go to talk to whoever the orange flow was, because I've actually seen and established that they were in the queue with me at this particular switch, and then I can go and find that there was some aggressive flow that was causing the problem all along. So just taking those four questions, which path did my packet take? Which rules did my packet follow? How long did it queue at each switch? And who did it share the queues with? It's very interesting that while there were four natural questions to ask, there's no network that I know of that can answer any of these. And so we're pretty seriously lacking in our ability to look in and see what a network is doing. And so one of the things that seemed almost natural once I saw people start to do it was, if you give them a programmable device, in various ways they'll try and answer these questions as a starting point. So there's something that you may have seen before, inbound network telemetry. It was a SIGCOMM paper of a number of years ago, and that it was attempting to answer this question. And there's now an int.p4, and there's a number of people that have implemented it in a variety of different platforms, both fixed and programmable, but we're all trying to get to these questions. And it's pretty simple. You just tell the switch to add the information you're looking for to the packets as they go through. Depending on what the particular protocols in the network, there are various places that you could put it. I would say that the location that this information goes into the packet, it may excite networking people, but frankly, it doesn't matter. It's a bit like getting excited about memory management or register allocation. Where you put the information, it really doesn't matter. I'm just interested in getting the information. Why do I worry so much about where it goes? I can move it around if the environment is programmable. In fact, the compiler can place it somewhere that seems convenient based on its knowledge of what the network is doing. That's really the right way to do it. So add the switch ID, the arrival time, matched rules, etc. You can see how this would answer, and then accumulate that information as you go. But the last switch, perhaps what you do is you extract that information and then send it down to something that will log, analyze, replay, and then potentially visualize that at some time later. You rip it out and then send the original packet on its way. This is one way that you can do it. This is the INT solution. There are many, many different ways you can do it. The chances that I am going to know the right solution are very slim because I don't run a big network. I would like to put those primitives in the hands of somebody that does, and then let them decide. And this seems to be the kind of thing that they're trying to do. From a P4 point of view, there's the P4 program that does the insertion. It's actually very simple, but of course that's just a consequence of the abstraction, and that you're not doing very much. You're just taking metadata and sticking it into a packet. Okay, the last thing I'd like to touch on is then why programmability now from an ASIC viewpoint. And I want to do this by slightly hand-wavy argument, but to give you a sense of why it is that the programmability is now free in terms of the relative to the fixed functions that we've seen in the past. And I would do this by reference to a sort of a series of pictures. You don't very often see digraphs, the pictures of the silicon themselves, and so these are ones that I've persuaded other people to let me use. This is a sequence of chips that were switching chips that are the fastest switching chips of their time. Now, if you mask out the area where the memory and the logic is, you're left with the serial I/O. And that serial I/O, which is the serial links that communicate to the outside world, it's typically about 30% of the switch chip area. That's true also of a Broadcom and Barefoot chips that are more recent. It's a pretty much constant percentage of the chip area. Now let's think about how this evolves over time. You know, why is it that for about 15 years it's always been 30% of the chip area? You would think that Moore's law would make it smaller, right? That's true. Moore's law will make it smaller, but we're greedy. We want to make them faster, and so we double the speed, counteracting Moore's law, and so it ends up being the same. So from one generation to the next, Moore's law makes it half. Our appetite doubles it to counteract Moore's law, and it ends up being about 30% of the area. So it's the same area for each generation. Now let's look at the other things that are on that chip. So 30% serial I/O, about 50% for packet processing, and 20% for packet buffer and traffic management, roughly. So let's look at that 50% for packet processing. About 25% of that is logic, and 25% of that is memory. Let's look at the memory first, which makes up the lookup tables and packet buffers. Well, you would think that Moore's law would make this half the size in each successive generation, right? Well, yes, but when you double the speeds of the I/O, people want packet buffers that are twice the size, and they want more lookup tables. So lo and behold, with each successive generation, exactly the same thing happens. Moore's law halves it, our appetite then doubles it again, and you end up with, overall, memory stays the same area from each generation, from one generation to the next. That leaves one thing that's left, about 25% of the chip, which is logic for packet processing. So the thing I'd like to point out first is this is the only thing that determines whether it's fixed function or programmable. Everything else is regardless. You have to have lookup tables, you have to have packet buffers, you have to have serial I/O. That's regardless of whether it's fixed function or programmable. So what happens to this portion? Well, if in each generation we were doubling the number of features, doubling the number of protocols, then yeah, you would sort of expect it to counteract. But we don't do that. In each successive generation over the years, we've typically added about 10% new features or fewer, maybe 5% in practice. So what that tells you is that that fraction, that amount of the chip, Moore's law is making it smaller, unlike the rest of it. And so over time, the logic, the portion of it that is determined to the function of the chip is going down. Put in a sort of a cruder way, what happens is over time, over successive generation, it does this. So if you look on one of these digraphs, what does memory look like? You've all seen digraphs of memory chips. They're totally uniform. What does logic look like? It looks like spaghetti. So by looking at the digraphs, you can sort of see what's going on. This is a picture from about 7 years ago. Ooh, that one's a bit more uniform, about 2 or 3 years ago. And this was a programmable chip that was produced by Spider, and this is a more recent one. You can see that they get more and more uniform over time as they get more programmable. But it's not because they're getting more programmable, it's actually because the logic is becoming a smaller and smaller portion. If you actually look inside the ones on the left, the two ones on the left, the Ericsson and the Barefoot ones on the right-hand side, if you actually zoom in, it's actually rather hard to find the logic. And the logic is almost entirely underneath the wires that form the pipeline. So here was the thing that it took me a while to realize is the logic is not just getting smaller, it's becoming free. And so the only thing that distinguishes a programmable fixed function is actually going away in terms of area, in terms of power, and therefore in terms of cost. In other words, there's no difference. So this, for me, this was one of those light bulb moments when if you can have programmability at the same cost, power, and performance as fixed function, of course you will, right? And so I actually now believe, as a consequence, that nothing to do with anything that I've done, nothing to do with it was a trend that was going to happen anyway. That it is absolutely inevitable now that over the next few years, switching chips will become programmable, and there will be no going back. That will be an irreversible trend. And that's just because it's free, relative to the fixed function. So, in summary, we can now make programmable chips as fast as the fixed ones. The difference in the chip area and power between programmable and fixed function is going away. There are actually now not necessarily too many protocols, but it's very, very hard to correctly verify the hard-coded functions in silicon. People who create those new ideas that I was referring to earlier, that Chang Kim always likes to refer to them as beautiful new ideas, they are owned by the person who writes the program. A little bit like when you write a Java program, Intel doesn't own your program, you do. If you want to change the behavior in a networking system today, I can guarantee it that your program, your feature will be owned by Cisco or whoever it is that provides the equipment or the chip vendor, because they've actually got to place it into their device. This isn't likely to work out very well because as soon as they have it, your competitor has it, so you've lost your ability to differentiate. So our current approach to building these systems is totally killing differentiation, innovation, invention, creation, which frankly I think is probably the biggest reason that networks are pretty much the same as they were in the past in terms of the underlying features and functions. So it has sort of killed the cycle of innovation. If you own your own ideas, then you're incentivized to keep doing them and enable you to differentiate relative to your competitors. Right? We all understand that, and this is just the way that it's beginning to happen now. And it's really, frankly, not very likely that the fixed functions that you find in a piece of fixed function switching silicon is likely to do what you want. Because let's face it, those features were put there by chip designers. And I've never met a chip designer that operated a very large network. So the chances that they've got it correct are actually pretty slim. if you put it in the hands of a programmer, whether they're a researcher trying out new ideas, like many of you are, or if they're somebody that's trying to operate a network in a different way than has been done before, then they're much more likely to be able to do that. So it really creates a level playing field, a solid platform, an abstraction layer in which more ideas will be built. And the idea I wanted to leave you with is this. For what you do every day, I doubt that almost anything that I've just said makes a material difference to what you do. Right? Because many of you are interested in either research in networking or programming languages or the intersection of the two. What I've just told you a little bit about is the context in which that sits and why you're in an area that is going to be here to stay, or why I think it's going to be here to stay. The way in which it will stay is because it's creating a platform or an abstraction layer that you and others can program. And that will be interesting for a while. But then it becomes solid. And then it becomes boring. And so what do we do in computer systems when a layer becomes solid and boring? Typically we go up. And then we create the next level of abstraction that sits on top that exploits that solid and boring substrate underneath. And this is where I think there is huge potential for which, frankly, I'm very unlikely to be the one that's contributing to those ideas, because the bigger the army of people that is actually working and building upon that, whether it's to derive programs from higher level abstractions, from higher level policies, or merely to provide a way to surpass or remove the P4 programming language, replace it with another one, whatever that happens to be. I imagine that it's someone in this room or someone working in this community that will start to do that, and I think there's enormous potential there. Thank you. It's actually beginning to look a little dark outside, so I'm actually going to put on a pair of these glasses and I'm going to walk outside. I don't know whether anyone else wants to.
Okay, so let's take a solar eclipse break. After the coffee break.
Oh, it's actually looking a bit strange. Right?
Break. And we have a door here, so you're welcome.